Nij, lower. 127, that is the official forecast written by the Weather Prediction Center this morning for the lower elevations of the desert southwest on Saturday, the 1st of August. It sits alongside a sentence most people will read straight past without stopping. Some values possibly close to monthly records for August. But the number that will do the most damage this weekend is much smaller than that. It is 80 degrees, the overnight low across parts of Texas that forecasters say will struggle to drop any further. A night that never cools is the exact part of a heat wave that causes severe health emergencies and fatalities, because the human body loses its single window to recover. At the very same moment, that exact atmospheric configuration is aiming a plume of tropical moisture straight at the hills of western Massachusetts, while holding 828,000 acres of uncontained wildfire across the Pacific Northwest under a high wind event scheduled for Saturday morning. One single shape in the atmosphere, 5 completely separate disasters unfolding across the continent. So what happens to the next 2 weeks if this pattern refuses to break? 600 decameters, that is the number. That is the entire story of the next 14 days, compressed into a technical metric that almost nobody outside a forecast office will ever say out loud, and that will not appear on a single television weather broadcast between now and mid-August. It appeared early this morning in a technical discussion written at 1:05 a.m. Pacific Time. It was buried in the short-term section, placed between a routine note about the marine layer and an update on coastal hazards. The forecaster noted that numerical models have shown remarkable consistency over the past week, projecting 500 millibar heights rising to 600 decameters over the interior deserts by Saturday. Then, almost as an aside in parentheses, the forecaster added the detail that actually matters: at or above the 99th percentile. Out of every 100 days in the historical record for that exact location at this time of year, 99 of them have a thinner, lighter layer of atmosphere sitting overhead than the one that will lock into place this Saturday. I want to be precise here because this is where standard reporting usually goes off the rails. That figure does not automatically mean the single hottest day ever recorded on Earth. It means something far more specific and structurally useful. It means the physical architecture of the atmosphere over North America this weekend is reaching the absolute upper boundary of its thermodynamic capacity. It is running near the extreme end of its own mechanical range. And when an atmospheric system runs at the absolute top of its range, every downstream process connected to it also runs at the maximum limit in ways that are rarely obvious and almost never linked together in daily headlines. So let me explain precisely what that means, because this is the central thesis of the entire situation. Right now, across the continent, there are hundreds of active weather alerts currently in effect. Decades of atmospheric data show that when a high-pressure ridge hits 600 decameters, it forces intense, large-scale subsidance. Sinking air compresses, and as it compresses, it heats up purely through mechanical pressure. This prevents cloud formation, locks in clear skies, and maximizes solar radiation reaching the soil. The dry ground then heats the air above it, forcing the column to expand upwards, which further reinforces the ridge. It is a self-sustaining physical feedback loop. Across the eastern region, that same blocking ridge holds a massive southward dip in the jet stream in place. Atmospheric moisture pulled from tropical source regions is forced up against terrain in New England, dropping 3 to 6 inches of rainfall onto saturated ground. Meanwhile, in the interior west, that same high-pressure dome suppresses overnight humidity recovery, keeping dead forest fuels primed for explosive fire growth. This is not a collection of isolated weather events happening by chance in the same week. It is a single, massive planetary wave locked in position over the North American continent. The ridge is parked over the west, the trough is parked over the east, and the interface between them is generating relentless precipitation and high wind. The core question that will define the next 14 days comes down to a documented split in the primary forecast models. Will the approaching northern Pacific trough coming across western Canada be strong enough to break the northern flank of this ridge, Or will the heat dome absorb the energy and expand eastward into the heavily populated corridors of the continent by the second week of August? In the early hours of 29th June 2021, a single automatic weather station in Lytton, British Columbia, recorded a surface temperature of 49.6 degrees Celsius. It was a value so far outside the historical distribution for Canada that if you plotted it on a standard bell curve of summer maximums dating back to the start of national record-keeping in 1840, it sat more than 4 standard deviations away from the mean. It broke the all-time Canadian high-temperature record, not by a fraction of a degree, but by 5.2 degrees Celsius in 48 hours. The next afternoon, the town burnt to the ground in less than 2 hours. The media coverage called it an unprecedented black swan event. But if you talk to senior climatologists at Environment and Climate Change Canada, or examine the historical upper air soundings archived by the Geological Survey of Canada, you quickly realize the headline framing was fundamentally wrong. What happened in Lytton, and what is repeating right now across the continent, was not a random meteorological fluke. It was the precise physical manifestation of a blocked, high-amplitude Rossby wave locking a 500 millibar height field above critical structural thresholds. To understand why the current ridge building across North America is so dangerous, you have to look at the historical baseline against which our civil infrastructure was designed. Modern municipal engineering in Western Canada, from the urban water distribution networks in Calgary relying on the Bow River, to the thermal tolerance of the hydroelectric transmission grids managed by BC Hydro and Manitoba Hydro, was built around atmospheric parameters established during the mid-20th century. Between 1950 and 1990, a standard North American summer high-pressure system across the interior plains and Cordillera operated within a predictable thermodynamic envelope. A normal summer ridge yielded 500 millibar geopotential heights averaging between 564 and 576 decameters. At these elevations, roughly 5.5 kilometers above sea level, the atmosphere exerted a stable downward pressure that allowed nighttime radiation to purge daytime thermal accumulation. Surface temperatures across the southern interior of British Columbia and the Canadian prairies occasionally touched 35 degrees Celsius, but the atmospheric column remained mobile. Rossby waves, the giant meanders in the high-altitude polar jet stream, marched from west to east across the Pacific Ocean at speeds averaging 30 to 50 kilometers per hour. Weather was transient. A hot spell arrived, built over 72 hours, and was promptly swept away by a cool maritime trough originating from the Gulf of Alaska. That mobility was the key structural assumption of 20th century grid resilience, agricultural planning, and wildland fire management. The Canadian Wildland Fire Information System was calibrated around the expectation that fuel moisture values in coniferous forests would recover every 48 to 72 hours as transient frontal boundaries crossed the provinces. What the current data shows is a structural departure from that historical baseline. When an upper-level ridge expands to 600 decameters, a height threshold rarely observed in the northern hemisphere prior to the late 20th century, it alters the fundamental fluid dynamics of the jet stream. Instead of behaving like a moving wave, the jet stream undergoes what atmospheric physicists call a resonant planetary wave amplification. The wave amplitude stretches north into the Northwest Territories and Yukon, while the phase speed drops to zero. The wave stalls. When a 600 decameter ridge locks over dry terrain, the mass of the air column above compresses the lower atmosphere at a lapse rate of approximately 9.8 degrees Celsius per 1,000 meters of descent. This is dry adiabatic compression. The air does not need an external heat source to warm up. The sheer physical weight of the sinking air column squeezes the gas molecules together, elevating surface temperatures mechanically. At the same time, the baseline conditions on the ground have shifted. Across the Canadian prairies and the American Southwest, soil moisture levels are monitored by joint satellite missions involving Natural Resources Canada and international partners. When soil moisture drops into the lowest 5th percentile, the latent heat flux, the amount of solar energy spent evaporating water from soil and plants, collapses to near zero. 100% of the incoming solar radiation is converted directly into sensible heat, raising the ambient air temperature. This creates the exact baseline mismatch we are seeing today. Our rail lines running through mountain passes are engineered for steel expansion thresholds based on historical maximums. When ambient air temperatures hit 42 degrees Celsius and direct solar radiation bakes the ballast, rail temperatures exceed 60 degrees Celsius, forcing Canadian National and Canadian Pacific Kansas City to impose mandatory speed restrictions to prevent track buckling. Hydroelectric reservoirs, such as Lake Diefenbaker on the South Saskatchewan River system, face double exposure. Accelerated evaporation rates combined with dwindling glacial meltwater from retreating sources like the Columbia icefield. The baseline of stable mobile weather patterns is gone. In its place is a rigid, high-amplitude regime where extreme atmospheric values persist over the same geographic coordinates for weeks. The tension in this episode comes from watching whether the current 600 decameter height field maintains its structural integrity against the incoming northern Pacific trough. To track where this goes next, keep your eyes on three specific indicators. First, the 500 millibar height reading at the Vernon Upper Air Station in BC. Second, whether overnight minimums in the interior valleys drop below 20 degrees Celsius. And third, the movement of the thermal trough along the eastern slopes of the Rockies. If those metrics stay elevated, the continental heat engine is not braking, it is simply preparing to shift its weight. A raw data plot from a radiosonde launched at 0000 UTC from the Environment and Climate Change Canada station in Kelowna showed a vertical temperature profile so distorted that the automated quality control script flagged it as a sensor malfunction. It was not a malfunction. The instrument, ascending through the troposphere at 300 meters per minute, recorded a temperature of 26.4 degrees Celsius at the 850 millibar level, roughly 1,500 meters above sea level. In standard atmospheric conditions across southern British Columbia, that layer should sit closer to 8 degrees Celsius. Sensationalist reporting often labels these setups as simple heat waves or summer domes. That framing is completely incomplete. What is happening inside this 600 decameter atmospheric block is a multi-stage thermodynamic feedback engine, and the physical mechanism driving it operates in three distinct phases. Phase 1 is large-scale mechanical subsidence. When a high-amplitude Rossby wave stalls over the continent, high-altitude air within the ridge is forced downward toward the Earth's surface. As this air descends, it moves from regions of lower atmospheric pressure aloft into regions of higher pressure near the surface. The physics of this process are governed by the ideal gas law. As pressure increases on a given volume of air, the gas is compressed. Compression converts potential energy directly into thermal energy without needing direct solar heating. Air descending under a 600 decameter ridge compresses and warms at the dry adiabatic lapse rate, precisely 9.8 degrees Celsius for every 1,000 meters of vertical drop. By the time that upper tropospheric air reaches valley floors in the interior of BC or the Alberta foothills, it has been mechanically heated by over 15 degrees Celsius before it even interacts with ground radiation. Phase 2 is the suppression of cloud formation and the collapse of boundary layer moisture. The broad downward motion of air under high pressure suppresses updrafts. Without rising air parcels, water vapor cannot cool, condense, and form clouds. The sky remains completely clear, allowing maximum incoming shortwave solar radiation to hit the ground unimpeded for up to 16 hours a day. Phase 3 is where the breaking point occurs. The complete shutdown of latent heat flux through land-atmosphere coupling. Under normal circumstances, when sunlight strikes trees, grass, and moist soil, a large portion of that solar energy is used up during evapotranspiration, the phase change of liquid water into vapor. This evaporative cooling acts as a natural air conditioner for the lower atmosphere. But when antecedent drought conditions reduce soil moisture below critical thresholds, such as the severe moisture deficits currently tracked by the Canadian Wildland Fire Information System across western provinces, there is no water left to evaporate. The latent heat flux drops to zero. As a result, 100% of the solar radiation becomes sensible heat, warming the soil surface directly. The superheated ground then radiates long-wave infrared energy back into the compressed layer of air resting right above it. The air warms, expands, and pushes the 500 millibar geopotential height level even higher into the stratosphere. The reinforced ridge forces even stronger downward subsidence, squeezing the air harder, heating it further, and locking the whole mechanism into a runaway feedback loop. This exact mechanism was confirmed during the extreme atmospheric events recorded by Ocean Networks Canada's offshore sensors and Natural Resources Canada monitoring stations. Standard predictive weather models fail during these events because their algorithms rely on historical parameterizations of land surface moisture that assume a functioning evaporative buffer. When that buffer vanishes, the surface temperature responds non-linearly, blowing past old historical operational thresholds. The mechanical reality of this heat engine is what makes it so destructive. To track whether this feedback loop continues to amplify or begins to collapse over the coming days, monitor 3 critical operational signals. First, the 850 millibar temperature profile on the evening upper air soundings from Edmonton and Stony Plain. Second, the relative humidity recovery percentage logged at midnight by remote automated weather stations in the Okanagan Valley. And third, whether the surface pressure gradient along the Pacific coast stays flat or begins to induce a marine push. Until a cool marine air mass pushes inland through coastal mountain passes, this atmospheric engine will remain fully engaged. A single red telemetry line on a monitor at the BC Hydro System Operations Control Center in Burnaby registered a sudden load spike at 16:42 Pacific Time. Within 4 minutes, urban electricity demand across the Lower Mainland reached 8,420 megawatts, a summer consumption level that matched historical winter peak loads previously seen only during sub-zero Arctic outflow events in January. Sensational headlines often frame these events as simple power grid alerts or temporary summer inconveniences. That framing completely misses the real crisis. What we are witnessing is the physical compounding of atmospheric force against the physical infrastructure that holds modern civil society together. When an atmospheric heat engine locks over a continent, it does not strike a single sector. It acts as a simultaneous force multiplier across energy grids, transportation corridors, municipal water supplies, and national supply chains. Consider the electrical infrastructure. High-voltage transmission lines, such as the 500 kilovolt bulk power corridors running from hydroelectric dams in northern British Columbia down to urban load centers, operate under rigid physical constraints. As ambient air temperatures remain above 40 degrees Celsius for consecutive days, the air surrounding the conductor cables loses its cooling capacity. Conductor lines carry massive electrical current, generating internal resistive heat. Under extreme atmospheric thermal loads, the metal expands, causing the massive overhead cables to sag meters below their safety margins. If a sagging high-voltage line touches vegetation in a mountain pass, it trips the circuit breaker instantly, cutting off power to hundreds of thousands of homes in seconds, while simultaneously igniting a new wildfire on the ground. At the exact same time, the hydroelectric reservoirs supplying those transmission lines face severe operational strain. In Alberta and Saskatchewan, major hydrological monitoring stations along the South Saskatchewan River system are recording streamflows dropping into the lowest 10th percentile for late summer. Lake Diefenbaker, a reservoir covering 430 square kilometers that provides drinking water to over 450,000 residents and irrigates hundreds of thousands of hectares of agricultural land, is seeing its surface elevation decline toward critical intake thresholds. If water levels fall below the physical height of municipal intake pipes, water supply systems enter cavitation failure. That means pumps draw in air rather than liquid, causing destructive mechanical vibration and forcing emergency municipal shutdowns. To picture the geographic scale of this impact, 828,000 acres, or roughly 335,000 hectares, of active, uncontained wildfire burning across western forestry zones represents an area larger than the entire city of Metro Vancouver 5 times over. When fires of this magnitude burn out of control near major transit corridors, they sever critical continental supply routes. Highway 1 through the Fraser Canyon and key Mountain Pass rail corridors operated by Canadian National and Canadian Pacific Kansas City are forced to shut down due to active fire activity or track buckling risks. When those rail corridors stop moving, container ships sit idling in the waters off the Port of Vancouver, unable to offload goods bound for eastern Canada. The economic friction accumulates at millions of Canadian dollars per hour. In urban areas, the real-world impact arrives quietly through Public Safety Canada's Alert Ready system, broadcasting extreme heat advisories directly to millions of mobile phones. But inside concrete high-rises lacking mechanical cooling, interior temperatures remain trapped above 35 degrees Celsius long past midnight, turning living rooms into dangerous thermal traps for vulnerable residents. To track how this systemic escalation unfolds over the next 48 hours, keep your eyes on 3 concrete indicators. First, whether Emergency Management BC or the Alberta Emergency Management Agency issues mandatory evacuation orders along primary mountain highway corridors. Second, the real-time operational reserve margins published by provincial power grid operators. And third, the stream flow rate logged at the Bow River Monitoring Station upstream of Calgary. If those river levels drop past historic low water markers while grid demand stays at peak capacity, municipal emergency measures will shift from voluntary conservation to mandatory structural cutbacks. 3 separate telemetry stations, one anchored in the deep waters off Vancouver Island by Ocean Networks Canada, one operated by the Geological Survey of Canada in the southern interior of British Columbia, and a high-altitude sensor station run by Environment and Climate Change Canada, all registered matching structural anomalies at 612 UTC. 3 completely different instruments across 2,000 kilometers of wilderness, all logging distinct physical manifestations of a single, massive planetary wave locking into place overhead. Commentators and online headlines will frame the coming days as either an apocalypse or a routine late summer hot spell. Both of those positions are entirely incorrect. The actual story is far more grounded, far more precise, and far more concerning. What is physically established by the raw data is that a 600 decameter geopotential height field has locked over the western interior, forcing severe mechanical subsidence and suppressing overnight thermal recovery across multiple provinces. What remains genuinely unresolved in the operational numerical weather prediction models is the precise decay rate of the eastern trough over the next 7 days. If the incoming low-pressure system moving off the Gulf of Alaska maintains sufficient atmospheric momentum, it will shear off the northern crest of the 600 decameter ridge over British Columbia and Alberta. That would allow a marine air mass to penetrate inland through mountain passes, dropping surface temperatures back toward normal seasonal averages. But if the heat dome absorbs that kinetic energy and remains stationary, the ridge will expand eastward, driving severe thermal stress across the Canadian prairies and into the heavily populated industrial corridors of Ontario and Quebec by the middle of August. To know with certainty which path this system takes, there are 3 specific, publicly accessible indicators you can check over the next 72 hours. First, monitor the daily 0000 UTC upper air sounding chart published by Environment and Climate Change Canada for the Kelowna and Stony Plain stations. Watch the 850 millibar temperature figure. If that value remains above 24 degrees Celsius, the lower atmosphere is remaining mechanically superheated, and the heat engine is continuing to self-reinforce. Second, check the daily fire weather danger maps published by the Canadian Wildland Fire Information System, specifically focusing on the fine fuel moisture code across the interior of BC and western Alberta. If those values stay above 92 without overnight recovery, the containment lines around active fires will remain under critical risk of sudden wind-driven blowups. Third, monitor the formal advisory pages of the International Joint Commission and provincial emergency management bodies, specifically looking for streamflow advisories along major transboundary water systems like the Columbia and South Saskatchewan river basins. If flow rates fall below historic 10th percentile thresholds, municipal water distribution systems and regional hydroelectric generation will face immediate operational curtailments. Until at least two of those three indicators show a measurable downward trend, the most realistic assessment is straightforward. The North American atmosphere is currently operating at the extreme upper boundary of its thermodynamic limit, and the physical buffer that usually protects our civil infrastructure has effectively vanished. We do not need to invent dramatic scenarios when the underlying physics of the atmosphere are already performing at the absolute limit of the system. Let us know in the comments below which region or municipality you are tuning in from tonight and what local conditions look like on your gauges. If you value precise, data-driven analysis of the systems shaping our environment, hit the like button and subscribe to stay updated on our next dispatch.